The purpose of this lecture is to review algebraic structures. And the reason I think this is important is as you study general relativity, particle theory, any of these really interesting cutting-edge scientific theories, there's a lot of mathematics that slips in that refers to algebraic structures, refers to groups. And of course groups are the big ones, but it also rings and algebras and all of these things. And it can become quite daunting to read texts with these words in it used very casually and not understand exactly what they mean. So I thought I would just review the definitions. I'm not going to do a lot of proofs of things, but I will go through some of the definitions. But an algebraic structure, you know, when we started out and studied a vector space, we said, hey, it's a set and then it has an operation. It has this vector addition operation. And we chose addition because we want it to be commutative, right? So we know that it's a commutative binary operation. It's a binary operation in that if this was the set V, it goes from V cross V into V, which means it's closed under this operation. That's a fancy way of saying it's closed, by the way. Right, you take any two elements of V, you execute this binary operation, which would be called addition, and you get an element of V. So it was a set endowed with an operation. But it also included yet another set, right, the set of real numbers, right, which were the scalars. So a vector space is an algebraic structure. And whenever we define an algebraic structure, you're going to see sort of the same kind of language. You're going to see we define one set or two sets. We define operations, and we define the operations using these Cartesian products, either from the set into itself, like this one, or from an element of both sets to somewhere else, right? The inner product, right, was an operation that existed on a set that was V cross V into, see if we call the scalars F. It was V cross V into F, right? So there's a certain kind of, so we offered up that as yet an additional operation that may have existed on a vector space. But we certainly know that scalar multiplication, which we defined with a little dot, was an operation from F cross V into V, right? And the vector space required that addition and scalar multiplication. And so by defining all of these things, that's how we created the algebraic structure known as a vector space. We define the sets involved and all of the operations that are involved. Some of the operations are inside one set. Some of the operations are inside both sets. The scalars, they have their own operations, right? The scalars have addition, subtraction, multiplication, and division when we're dealing with the real numbers, right, and the complex numbers likewise. So there's a lot of operations involved, and every one of these things added to the sum of all of these things together, the totality of all these things created the algebraic structure of the vector space. And that's how we're going to do it for all the algebraic structures. We're going to define sets, operations, and the operations will have certain properties, right? And then that'll define the algebraic structure, and then we'll build more complicated algebraic structures from simpler ones. Vector space is actually a pretty complex, pretty tricky algebraic structure. We're going to start much, much lower than that. Okay, so let's begin. We're going to start with algebraic structures that only require one set. One set. And this set I guess I'll call G, right? And the first algebraic structure is about as simple as you can get, and it's called a groupoid. And it's also called a magma. I don't know which is the newer or older word, if groupoid is older than magma or if magma is recent, not really sure. But it definitely, like all of these things, it starts, the groupoid is the set, but the set has to have one specific property, and that property is the property of being, of having a map. It has to have a map. So it's a set with a map, and the mapping will be, we could call it a multiplication, set multiplication, and it's a mapping from G cross G into G, which makes perfect sense. There's only one set involved, so there's really only one place for this mapping to go, and there's only one possible domain for a mapping. If you're only dealing with one set, you've got one domain, one place it can go, and we'll call it multiplication. And the fact that this is the mapping implies I can take any element of G, put it here, any element of G, put it there, and I'll get an element out. And of course, this is going to be, say, element G1, element G2. That shall map into some other element. And it doesn't have to be a unique element, by the way. It could be G1 or G2. There's no rules or restrictions about it, but the point is when you write it this way, it is closed, right? It is closed, meaning that you'll always get something in G. You'll never get something like this, where you get something that's not in G, some set A, because we don't have a set A involved, right? That would require us to introduce another set. So closure under this groupoid operation is the only thing that's required. And once you have that, you've got a groupoid. So to give an example of a groupoid is actually pretty tough because, for example, a vector space is certainly a groupoid, right? Because we know a vector space has addition, and that addition certainly satisfies this rule. But a vector space is so much more than a groupoid. So it's always nice to find examples of these algebraic structures that are no more complicated than they absolutely need to be. For example, there's nothing about this that says it has to be commutative, right? There's nothing about this that says it has to be associative, right? Doesn't even have to be associative. There's nothing about this that says you have to have an identity element, right? And there's nothing about this that says every element must have an inverse, which makes perfect sense because if you're not required to have an identity, you can't be required to have an inverse. So it'd be kind of fun to find an example of a set and an operation that does not have any of these properties. And best example that I know of is the example of binary trees. And a binary tree would just be any kind of collection of sticks and dots that look like a binary tree. Here's a good example of one. And we might label this P0, P1, P11, P12, P1, P121, P122, right? And then this would be, that's P1, maybe that would be P2, and that'd be P21 and P22, something like that. So a binary tree, if we consider the set of all binary trees, the set of all binary trees, and then we have to define some kind of, if we call that our set B, right? We have to define a map that goes from B, from the Cartesian product of B and B into B. So it's some function that takes ordered pairs, so it would be a function acting on an ordered pair, binary tree 1 and binary tree 2, and it returns a binary tree. So a good example of that mapping would be if I had a binary tree here, for example, and then I had another binary tree, say that one, and I wanted to multiply them together with phi, so it's sort of phi operating on those two binary trees. What I do is I just add another point, right, and I connect the two binary trees from that point. So it would look something like this, right? And if I did that, it's certainly not a commutative process, and it's not an associative process. It has no identity, right, because the identity would require that I should be able, if I could put the identity in one of the slots, I should get the other tree back. But anything that I put in this slot is going to require the tree to get bigger, right? So there's no identity. If there's no identity, there's no inverse. So this is a good example of something that might be a pure groupoid. There's other examples too. Concatenation of strings is another popular example, but we don't use groupoids too much, but it is sort of the basis of our next algebraic structure, which is called a semigroup. Okay, so now we're going to talk about the next algebraic structure in complexity, which is called the semigroup. And the semigroup is a groupoid with a binary operation that is associative. And of course, remember, all these things can be more than what I'm writing down here. It can be a groupoid with a binary operation that is associative and commutative and has other properties as well. Just as a groupoid is still a groupoid if it's associative, like that's what I said over here, right? This is an example of just a groupoid that has only got this closed mapping, but it's not associative or commutative. But it could be associative or commutative. So these are inclusive. So a semigroup is a groupoid that is associative. And a good example of a groupoid, or a semigroup, is imagine if we took some letters, say A, B, C, and D, and we started talking about making strings of these letters. So a string might be B, B, C, D, A, or A, B, or D, C. Those would all be strings. And then if we considered the set of all possible strings, right, then we could make the multiplication operation, which would be, let's call this the set S, S Cartesian S to S. We need that because a semigroup is a groupoid, and a groupoid must have a closed operation which we're calling multiplication. And it turns out if you do this, of course, I mean, it doesn't take too much to see that if you had a string BCA and a string A, or a string ADB, and you had a string AAA like this, and you did this group multiplication, certainly the result, if it's concatenation of strings, right, this concatenates to AAABCA, and that ADB, that will certainly concatenate to the same thing as if I did this grouping first, right? It doesn't matter whether I group it to, with these two first or whether I group it with these two first. So it's associative, right? But it's not commutative, right? Because clearly AB times CD is not CD times AB. So it's not commutative. And it also doesn't have an identity. There's no identity string. Every string has at least one element because I have not defined an empty string, right? So if S does not contain an empty string, there's no identity element, so I can't say AB concatenated with the empty string equals AB. I don't have that. So with no empty string, and even if there was an empty string, I don't think you could ever, there would be no inverses, right? Because AB, there's no other string to put here that would give me the empty string. So, but if I did add the empty string, I would have a set that was a semigroup with an identity, So anyway, that's a good example of a semigroup that's just a semigroup. But there is this important thing that kind of sneaks up that first introduces itself here in the semigroup, which is you can imagine the semigroup does have an identity. Let's say it does have an identity. So the problem is this is not a problem, but this is an ordered pair, right? This refers to an ordered pair, A, B. So there is the question of whether this identity is an identity for all elements. Let's say let me create a. Let's say the string we just give the name. The string is alpha, right? You could have an identity where the identity times alpha equals alpha, or you could have it to be alpha times the identity equals alpha. It could be one or both. Now in this case, with the empty string and concatenation, both of these are true. But you could have a semigroup where only one of them is true. The identity only works on the right side, and it doesn't work on the left side, right? In which case, it only works if the identity itself is on the left side. In which case, it would be a left identity, or otherwise, it would be a right identity. And you could get a two-sided identity if it's both left and right. So phi here is a two-sided identity. And this actually becomes a point an important point for things that are not commutative. If things are commutative, then you always will have a two-sided identity. But when they're not commutative, you kind of got to keep track of the left and right nature of things. In books, when you read about these and they do a little diversion into mathematics, sometimes you start seeing left and right pop up, and that is usually a sign that there's an issue about commutativity. Although not always. Sometimes you have non-commutative groups, but you can still define an identity that is commutative. Because for a semigroup to be commutative, it would have to be true for every two pair of points would have to be commutative. It would always have to be that AB equals BA. But you could have it so that this is not true for everything, but it is true for the identity, right? In which case you could have a two-sided identity for a non-commutative group. Okay, so that takes care of the semigroup. So we'll now go to the next level of complexity, which is called the monoid. So our next object is the monoid. Right? The monoid is, well, it's definitely a magma, right? But it's also a semigroup, and it's a semigroup plus a two-sided identity. So a monoid is, it's going to be a set, we'll call that M, plus a operation from M, Cartesian M to M, that is associative, right? So that gets us all the way from here to there, right? And then we have to add that there is an element in the thing, I'll put it in red, we'll call it E, such that E times any member of the monoid A equals A times E, which equals A, right? So it's got this two-sided identity. And if you have that, you have a monoid. So once you have the monoid, you start, this gives you the ability to start talking about inverses, right? Notice the monoid doesn't require that every element have an inverse, right? We don't demand that there's an element which we can call A inverse such that it's going to equal this identity. That may or may not be true. The monoid opens up the door for that to be possible, but it's never, it's not definitely guaranteed, right? So for example, with our string situation, right, I took that set S of all possible strings, all strings, let's just say binary strings, so it's just 0 and 1 is our total, all 0, 1 strings, right? So it only contains 0, 1, and there's no null string, right? No null string. So that isn't even a monoid. But what we do to make any semigroup a monoid, we just say, okay, look, I'm going to create the null string, and I'm going to define the null string times any element of S, say SE, well, let's go with A since I used A. The null string times any element of A, and any element of A times the null string is going to be A. I just define it that way. And then if I create S union this null string, I guess the set that contains the null string, that is going to be a monoid because I've created this identity. But I still don't have inverses, right? I'm not going to, that doesn't give me inverses. It just gives me an identity element. But this is definitely down our road to getting inverses. And inverses are important because that's getting down our road to the notion of division, which is a very advanced notion, as you can see. It requires a lot of pieces. All right, so that's a monoid, and this is a good example of a monoid. You know what, perhaps an even better example of is the natural numbers, right? The natural numbers, 0, 1, 2, with the operation of regular arithmetic addition, right? Well, there's your identity, and it's definitely two-sided, right? A plus 0 equals B plus, equals 0 plus A. So it's a two-sided identity. So it's definitely a monoid. And again, there's no inverses, right? Because 1 plus -1 equals 0, but -1 is not an element of the natural numbers. So that's probably even a better example of a monoid. Or should I say a better example of a minimal monoid, a monoid that has a minimal amount of structure. In fact, this isn't totally minimal because this operation is commutative, right? A monoid, it only has to be associative. So this is a little bit super minimal in that sense. But it does show up, and it's an important part. It's an important structure that we need to understand ultimately the next more sophisticated algebraic structure. Okay, so before going on to the next one, I want to emphasize this point about invertibility. This doesn't capture all of what being invertible actually means, but the fact that the identity exists means it's possible to have something that we could call an invertible element. And so how would that actually work? So if our monoid is M, right, so this is our set, that's the monoid, and our monoid operation is this, say, star, which we know is associative and has an identity, a two-sided identity. What we want to do is define the notion of being invertible, and the way we define it is we say that there's an element in X. So we pick just one element, an element in M, and we just pick one element of N, we call it X. And we say that X is invertible if the multiplicative operation on some other element Y equals the reverse, the commutation of it, the Y operating on X, which equals E. If we pick an X and we can find a Y such that this is true, then we say that X is invertible, or X has an inverse. And we can also say that Y is the inverse of X, and so we can write Y equals the inverse of X. And also, if X has this property, meaning that not every X in M is going to have this property, it's not going to be true for everything in this set, but if it is true for that guy, then X is a unit. I call it a unit. So a unit element of a semigroup with a two-sided identity. So a unit element of a semigroup or of a two-sided identity, which is a monoid. So a monoid is allowed to have units. Now a monoid doesn't have to have a unit, as I've already said. Not everything has to have an inverse. Not anything has to have an inverse in a monoid. But if it does, this is what we mean by an inverse. This is what we mean by an inverse. Now, if X is a unit, then the inverse of X is unique. And the way we can understand that is, say X is a unit and Y is its inverse. Now I'm going to skip writing the multiplication symbol in there because we know it's got to be the monoids operation. So X times Y is going to equal Y times X. Imagine that there was a different Y that satisfied the same property, that there was a second inverse. So that would mean that there's some other number out there, or some other member of the monoid out there, X times Z, which equals Z times X, and all of this equals E, right? And if that was the case, if that was true, if there was this second one, obviously what we're going to do is we're going to show a contradiction, but let's look at Z. Z definitely equals Z times E by definition of the identity, which definitely equals Z, let me put a little line through the Z's here, times XY, right? Because I can just substitute XY for the identity without much trouble. But that is going to be ZX times Y, right? And that's going to equal EY, which is going to equal Y, and so ultimately Z equals Y. So if this is true for a certain unit x, then y is unique, right? Y must be unique. Now notice that in this process of proving that, notice that to go from here to here, we used associativity, right? We went from this to that. And that's why associativity is so darn important, right? When we go through this process of going from a magma up to a monoid, the first thing we ask is that the group operation be associative. And a lot of proofs just don't work without associativity. Commutativity doesn't show up till much later. We don't start demanding commutativity till later. But associativity, we want that one right away. And that's because very simple proofs like this don't make sense without commutativity. You can't prove the uniqueness, this uniqueness, without associativity. Like I said, commutativity comes later. Okay, so what's next? Well, next is the big one, the one that we probably learned first, and most of you probably already know, and that's the group, right? So we've gone from groupoids to semigroups to monoids and to groups. And these are inclusive, right? Every group is a monoid, every monoid is a semigroup, every semigroup is a groupoid. So, but the group is usually the one we learn the first because it's probably the most interesting abstract algebraic idea out there, and it certainly is the most applied to physics, right? The one that you need the soonest in physics, right? You can use them in quantum mechanics and classical mechanics, certainly particle physics, all that uses groups. So how do you get from a monoid to a group? What is this path? And that path is pretty simple. Every member, every element of a group is a unit, right? So we have our group, which is the set. We have our operation, which we almost always call multiplication. Well, I shouldn't say that. We don't almost always call it multiplication. When it's abelian, we call it addition, right? When it's commutative, we call it addition. But we don't require commutativity, so we're certainly not going to use that in our fundamental definition of a group. But we have a group, we have our operation. We know that it is associative because we have the semigroup. We know that there exists an identity because it's a monoid. But we also know that for every element x in G, we have x inverse, which is also in G, and x inverse equals the identity. And that's true for every element in G. So when we have all of that, we have a group. Emphasize again, the group does not have to be commutative, of course. It can be a non-commutative group, but it always has to be associative because it's a semigroup, and that's the definition of a semigroup, is that associativity. So, but this property that every unit is every member of the group is a unit. Is another way of saying every member has an inverse. And the reason that's important is now you kind of are beginning this notion of divisibility, right? Because once everything has an inverse, you can kind of say things like A times B is one thing, but A times B inverse sort of starts looking like A divided by B. So we're kind of talking about that sort of concept now. And that only can make sense if everything is invertible. I don't want to literally use this notation for any purpose, but that's sort of where we're headed. And by the way, in all of this, we're talking about closure, right? Every time we do this, we need to know that we're dealing with a mapping from G cross G into G, so everything is closed, right? Closure is part of this whole narrative, but it comes all the way back from the beginning here. Closure is like the very first thing, and then and the existence of this closed operation flows through the entire thing. Now, as far as examples of groups, there's just so many. I think I'm not going to bother giving too many examples of groups. I mean, you have the groups of the integer z form a group under addition, right? That's just your sort of obvious, super simple group. We'll be talking about continuous groups in general relativity, and pretty soon when we talk about the Lie groups and Lie derivatives associated with, the Lie derivatives involve the Lie groups of transformations or continuous transformations, continuous single parameter transformations. Those are all groups. And ultimately, this becomes just such a fundamental concept in physics. But hey, we got there from the bottom up. Usually, by the way, this is where we start, right? So usually when you learn about groups, you just learn, hey, it's a set with a property that's associative, has an identity, and every element has an inverse, and it's closed under the operation. That's the definition we learn right away. And of course, we built it up. Okay, so after a group, that exhausts our basic elementary algebraic structures that have one operation on one set. Now, there's, if you looked up algebraic structures, you might find dozens of them, and that's because each one of these has its own subclasses of things. Like a semigroup that's commutative is called a commutative semigroup. And there's all sorts of different types of monoids, and they all have special names, sometimes given but to the name by the guy who discovered it or the woman who discovered it. But none of them actually get additional names, right? Groupoids become semigroups when the most important thing is added, associativity. Semigroups become monoid when the next most important thing is added, an identity. Now, there actually is another track that leaves groupoids and gets to groups through another way that has other names of things. One of them is called a loop. There's an algebraic structure called a loop, for example. But those are so non-standard, and they don't show up in general relativity textbooks or mathematic textbooks that support them very often. So I'm not going to go into that other route. So, but what is next? We've exhausted one operator. So now we're going to talk about algebraic structures that have two operators. And the first most elementary structure with two operations, I said operators before I meant operation, is the ring. And this one actually does show up quite a bit. So the ring. And the ring, we'll call our ring R. And as always, it is a set. We're still dealing with only one set, right? But now we have two operations. And the operation on the set that matters is an operation we're going to call addition. And addition is, like always, it is an operation from R, from R cross R into R. Now this is not real numbers, right? This is the ring, the set of rings. So there's right off the bat, there's your groupoid, and addition we know is going to be associative and commutative, right? So this is going to be up to that point being associative and commutative. That means we've got a commutative semigroup, right? A commutative semigroup. And then on top of that, we make sure that there is an identity and everything has an inverse, right? So in the end, what we actually have is a commutative group. We have an abelian group. And the reason we use the addition symbol is because it's commutative. When you have an operation, a group operation that is commutative, it's very, very common to use the plus symbol. You don't have to, though, right? We could have defined this with, a regular old star multiplication or any symbol at all. But for rings, it's very, very common, and matter of fact, it's almost universal, to use a plus symbol to show the commutative group operation. So a ring right now has just started out as a commutative group, as an abelian group. But remember, it has two operations, not just one. So, and the inverse for any element of an abelian group is always given by minus a. So a plus minus a equals 0. And 0 is given as the identity element, right? So when we start using this plus sign, we actually import a lot of different things. We import, instead of saying A inverse like this, we actually write it in the way you would for an arithmetic problem. And A plus 0 equals 0 plus A equals A, of course, is how you identify the identity when you're using the language of addition. So, but what about the second operation? Well, the second operation is that we will use the multiplicative symbol for. And it is also an operation from R across R into R. And it has to be because that's really the only place to go. We only have R available to us. So the second operation is also R across R into R. And the second operation is going to be associative. And it's going to have an identity. So the second operation means that this group R, so R is a commutative group under the first operation, but it is merely a monoid under the second operation, right? So you can kind of see how these things are built up of each other. R is both a commutative group and a monoid, but it's a monoid for two reasons. The first reason is that every commutative group is a monoid, right? Because that's how this whole pantheon works. So every group is a monoid, including commutative groups. So that's one reason it's a monoid. But it's also a monoid under this other operation. It has a separate operation where it's only a monoid, or it only has to be a monoid. Again, you can add stronger constraints to these and they'll still be a ring. You don't stop being a ring because maybe there's a few inverses here or something, right? So, or even if this was a group, a ring could still be a group under this multiplication property, and it would still be a ring, but it would be something even stronger. Anyway, so, but in order to define a ring, you need to be a commutative group, and you need to have this other element of being a monoid. And then you have to demand one other thing. You have to demand distributivity? Distributivity? Is that the right word? You have to demand that it be distributive. Let me just do it that way. You have to demand that it be distributive. So you want it to be, you want the monoid operation to be distributive with respect to the addition operation. So you want to be able to write a monoid operation be abelian group operation. You want that to equal a monoid abelian a monoid, like that. You want that to be true. And it's got to be true in both sides, because remember, this doesn't have to be commutative. So it's got to also be that B plus C dot A equals B A plus B, plus C A, right? So it's got to be distributive. The monoid operation must be distributed under the addition operation. And that gets you a ring. So now we've got two operations. Two mappings, I guess is the better way to say it. So, of course, the classical example of the ring is, let's see, the set, let me go, 0, 1, 2, 3, I guess 3, 4, 5. Let's try that. We'll call this set, we'll call that set Z6. I think we have to call it n plus 1, right? And the addition operation is going to be from Z6 cross Z6 into Z6. And it will be defined by, let's say, an element of Z6. Let's say A and B are elements of Z6. You'll say that A plus B equals, now this is the additive operation in Z6. That's this guy right here, right? In fact, you know what I'm going to do? I'm going to change the color of it. Again, sometimes I like to do that. A plus B is this, and that's going to end up equaling A plus B mod 6, modulo 6. And in this case, I leave it black because I'm actually talking about regular addition of two numbers, right? So that satisfies addition. It's certainly, it's an abelian group. This is going to be an abelian group under this addition property. It'll be completely closed, right? 5 plus 1 is 0, 4 plus 3 is 1, 2 plus 3 is 5, 1 plus 4 is 5, 5 plus 4 is 3. So, I mean, it's all closed. And everything has an inverse, right? Because, let's see, 3 plus 3, so 3 plus 3 equals 0, right? So 3 is its own inverse, right? And there's a word for that. I think it's idempotent. So 3 plus 3 is its own inverse. 5 plus 1 equals 0. So 1 is the inverse of 5. So there are additive inverse elements. So it's a group. It's an abelian group. Has an identity, of course, because 3 plus 0 equals 3. So it's got an identity, and it's an abelian group. It's got inverses. So it's in a group. So it's a group under this addition. But what's also nice is that it's a monoid under multiplication, where we define the group multiplication by again, well, it's Z6 cross Z6 into Z6, and A group multiplication B equals integer A multiplied standard integer B mod 6 again. And in this case, you have you definitely have a unit, right? Because 1, well, you have an identity, which is 1, right? So, 3 times 1 equals 3, and 1 times 5 equals 5, right? That's all good. And everything has an inverse, right? Well, actually, inverse is not required, right? Because it only has to be a monoid, right? So it's good. And it's important that it's a monoid because not everything does have an inverse, right? The 0 here, of course, doesn't have an inverse. So you don't need an inverse for everything. You just need an identity to establish the fact that it's a monoid. Is it distributive? Yes, and the answer is yes. It will be distributive too, right? So you can check that yourself, but it will be distributed. This is a really good example of a ring. But a much more important example of a ring is the ring of matrices. So imagine that we are dealing with 2 by 2 matrices, just to make it simple, entries A, B, C, and D. Notice that in order to define this ring, the ring is going to be the set of all these matrices. But in order for this ring to make sense, I have to tell you what these things are, right? So it turns out that those things can be any element of some other ring, right? So let's just consider them, say, just the ring of real numbers, right? Real numbers turn out to be a ring. Real numbers are even more than a ring, actually. They're a field, which we'll get to in a minute. But let's just talk about a ring of matrices made of the ring of real numbers, or the field of real numbers. So, in other words, A, B, etc. are all elements of the real numbers. So we'll call that our ring here. I'll erase that R so it's not confusing. And so under regular matrix addition, you've got the abelian group. So R is an abelian group under matrix addition, and it's a monoid under matrix multiplication. So that's good. It's non-commutative, so it's going to be a monoid without any flourishes. It's non-commutative under the monoid is not. It's a non-commutative monoid, And the identity for the monoid will be the standard 2 by 2 identity, 0, 1, 0, 1. Now what is interesting is, remember, there's an identity for the addition element, right? And that identity is 0. And then there's an identity for the monoid, which we could write as sort of this fancy 1, right? You could, in fact, write two different identities. You could say, well, the 0 is very telling, but if you have two different operations, you sometimes have to label them. So you might label this as the identity under plus, and this as the identity under the monoid multiplication. You would never do this, because whenever you use the addition symbol, you always want to use a 0. But remember, 0 is an element of the ring, right? You do have a 0 element of the ring. So this brings up this interesting possibility that I could have, say, I'm trying to think of one that is really obvious to do. I guess 1, 0, 0, 0. I could say I took this. That's certainly an element of R, right? And I think if I multiply it by this, right, don't I end up with 0? Yeah. So you get 0, 0, 0, 0 like that, something like this, right? And let's see, 1 times 0, that'll be 0, and then, yeah. So this is two non-zero elements that, when multiplied together, kind of give you a 0, which is interesting, right? I mean, you're basically saying A times B equals 0, but neither A nor B equals 0, right? So this implied here is the monoid multiplication. The monoid multiplication is what we're, let me make that a bit clearer. Neither A nor B, not element of, equals 0. So the monoid multiplication gives you the additive identity. And so this is what we might call a zero divisor. And you can have a left and right zero divisor because, again, it's non-commutative, right? So, so an element A is a left zero divisor if there exists some element X, I guess, in the set where that's true. A is a right zero divisor if there exists an element Y, such as that's true, right? And so the possibility of a zero divisor is actually exists now for rings because you have these two operations. One, the abelian group gives us what we want to call a 0, and the monoid operation gives you this sense of multiplication. Also, I should point out that you can create the idea of a ring where you start weakening this thing, right? This is supposed to be an abelian group, which demands you have an additive inverse for every element in the ring. But you can get rid of that additive inverse requirement, and you could create something that's a little weaker. And I think the word for that would be a semi-ring, right? So there's this idea of a semi-ring, just like there's an idea of a semi-group, right? And sometimes a semi-ring is called an RIG, where they take out the N, and I guess the N stands for negative, right? So there's no negative, so they turn it into a rig. And likewise, you can get rid of the monoid requirement and just return it to return the monoid back into a semi-group, which means you eliminate the requirement for the identity. You take this identity away, in which case you're getting rid of the I for identity, and you end up with an RNG. So, like I said, there's so many different variants on all of this, but the ones we're learning are the important ones. Semi-rings are I don't think I've ever actually seen a semi-ring that I've needed to use in physics, but rings definitely show up from time to time. Okay, so what's next? Well, where are we? We created a ring, so now we're going to create a division ring. So this is actually, it seems like it might be just a subtype of ring, and I've already been dismissive, like a commutative ring. I didn't highlight that as a special class, although it is a class of ring. A division ring is actually a very important subclass of ring that we've got to focus on. And the idea is that the ring was built out of an abelian group, which we use the operation, which the operation was plus, and this monoid operation. But remember, a monoid only has an identity, which I'll just call by that fancy 1. It does not demand inverses, right? We already learned that about monoids. So therefore, a ring does not demand to have multiplicative inverses. But for a division ring, every element has a multiplicative inverse. So for a division ring, every element is a unit, except for 0, right? If every element had a unit, but I didn't have this caveat, right? If every element had a unit without any caveats, then it would be a group under the monoid operation, right? Because monoids are associative, then there would be an identity, and every element would have an inverse. So the ring R, right, like that, would be a group under the addition, and it would be a group under the monoid. But it's not a group under the monoid operation, because the additive identity, the 0 that's drawn from this abelian group, does not have to have an inverse. That is, it does not have to have a multiplicative inverse, right? It has its own inverse, like 0 plus 0 equals 0. So in some sense, 0 is its own additive inverse, but there is no 0 dot 0 inverse, which equals 1, right? There's no multiplicative inverse for 0. Another way to say that, well, let's see, every element except for 0 is a unit. And it turns out, it's interesting, the set of all units in a ring, right? I'll call that RU, right? The set of all units in a ring R, right? Not the real numbers, but a ring R. That turns out to be a group, interestingly enough, right? That turns out to be a group because 0 will never be a unit. So, but that's a little bit in the weeds. But so a division ring, now we start allowing ourselves to do division. And hey, in division we learned in regular real numbers, right? We know that you can't divide by 0, right? So you can't write 1 0 inverse. So that's not unusual that you would exempt 0 from having an inverse. Every other number, every single real number has a multiplicative inverse except for the real number 0. So that's totally logical. A ring formalizes that concept in an abstract way, where now all we talk about is some set with these properties. We don't specify that it has to be a real number, or it has to be real numbers or anything else. But a division ring is the last step we have before we get to the big one, which is called a field. Probably one of the more relevant division rings that we care about. Again, looking for an example that is a division ring, but not this new thing we're going to talk about in a minute called a field. The best example for that is the quaternions. And the quaternions is the set of, well, the set of all quaternions, where a quaternion is a real number A plus a real number times this little thing called I plus this real number little thing called J plus a real number times this little thing called K, where I squared equals J squared equals K squared equals I, J, K, which equals -1, right? So this is sort of, it's an expansion on the complex numbers. I'm sure you've seen it before, but if you can add two quaternions together by just adding the real parts together, the I components together, the J components together, and the K components together, and that addition has perfect inverses, right? Just use the A, B, C, and D, by the way, are real numbers, right? A, B, C, and D are all elements of the real numbers. So you can make additive inverses very quickly, and then 0 exists without any trouble. So you definitely get to be an abelian group under addition for quaternions. Multiplication of quaternions is just simply A plus BI plus CJ plus DK. You just multiply that. Let's see if I can move this to someplace a little more. So if I took that and I multiplied it by E plus Fi plus GJ plus HK, then I just do straight up multiplication, and I just keep in mind every time I see I squared, J squared, or K squared, I replace it with -1. If I see IJ, I can replace that with K, and there's a little multiplication table that can be derived by this last part without any trouble. I guess you would do IJK equals -1, so IJ K squared equals -1 times K, so minus IJ equals minus K, so IJ equals K, right? So you can derive all of the little products without any trouble, and so you can get multiplication, and that becomes your multiplication of quaternions, and it turns out that they have multiplicative, the quaternions actually have multiplicative inverses. Every quaternion is a unit, except for the 0 quaternion, which is not a unit, and it doesn't have to be. So the quaternions form a division ring, because it's not only a ring, because it satisfies these two properties. It has the abelian addition and the monoid multiplication. Okay, so now we're going to talk about the last one, which is a field. So of course it doesn't hurt to, we had our rings, which were built out of a group, an abelian group, right? I did say that abelian is just a synonym for a commutative, right? It's got a group and an abelian group and a, well, it is an abelian group, and it's also a monoid under the multiplication. It's abelian group under addition. That gave us set us up to make a division ring where everything is a unit, everything but 0 is a unit, which means everything but 0 has a multiplicative inverse under the monoid rule. But because 0 doesn't have it, the division ring cannot be a group. And the field is just one more step. The field just says, now a field is the next algebraic structure, and all that says is that the monoid multiplication is commutative. You're dealing with a commutative monoid, right? So you're just going back here and you're adding another condition or another property to the monoid multiplication. And when you have that, you have a field. And once you have the field, you're pretty good, because you're talking about something that has addition, which implies subtraction through the inverse. It has multiplication, which implies division through its inverse in a logical way that doesn't include the additive inverse or 0. And it's commutative and associative, of course. Everything's associative, but it's also commutative. And the field, the big two fields, are the real numbers and the complex numbers. Those are both fields. The quaternions, which you can tell are very related to the complex numbers, not a field because it's not commutative, right? A quaternion, A plus BI plus CJ plus DK, right? If you multiply that by another quaternion here, that's totally different than if you do it this way. So it's not commutative. And therefore, the quaternions are not a field. In fact, you could actually call a field a commutative division ring, right? Commutative division ring, right? So it gets an extra word, but a commutative division ring is a field. It's hard to think of a single word that can get from ring to division ring, though. It's like a ring with a unital, well, a ring where everything's a unit is kind of hard to say, but we have a word for a commutative. So a commutative division ring is a field. And another way to kind of look at a field is, imagine we have a field, right? So we know it's a set, and we know it has the plus, we know it has this monoid, commutative monoid multiplication. We can actually say it is, F is an abelian group under here, right? We know that by all these definitions we've been repeating over. But we can also say that F without the zero element is also an abelian group under this monoid multiplication. So F minus the abelian identity, or minus the abelian group identity, is also, well, I should say this set, which is not the same as F, right? It's F minus that, is an abelian group under the monoid. So this monoid multiplication, which I keep calling it the monoid multiplication, I think the more standard language is you have the addition and the multiplication of a ring. The ring has an addition property and a multiplication property, not the abelian group addition property and the monoid multiplication property. I fell into that language by going through the logic from starting with groups and monoids and defining everything. So the field, right, if you have a field, it really is two abelian groups. The field itself is abelian under addition, and the field minus the addition element turns out to be an abelian group under the multiplication. And the reason that's the case is because to be a field, we demand that the multiplication property be commutative. And that is a field. And the two big fields we use are the real numbers and the complex numbers. And from a field, we will, that is how we will ultimately construct our vector spaces. I told you we did real vector spaces and complex vector spaces, but a vector space can be over any bin of scalars that is a field, right? Now, ultimately, there's a definition, an older definition of a vector space that says, no, any division ring is good enough. And we'll call a vector space the bin of scalars just has to be a division ring, in which case you could have a quaternionic vector space, right, under that notion. But this is a bit semantics because you can form a something we call a module with the quaternions, and you can form a vector spaces with reals, and as long as you know what you're doing and understand the properties that you're dealing with, you're in good shape. But there is an older definition of vector space that says all you need is a division ring to form scalars. But that's not the modern definition. The modern definition is almost universally a vector space has scalars that come from a field. So you can always add your scalars, subtract your scalars, multiply and divide your scalars in a way consistent with the real numbers, meaning you can't divide by zero. Okay, so that completes the review of the first phase of our algebraic structure review. These are the things that all involve one set and either one or two operations. So the next survey of this topic is going to involve two sets and operations associated with those. All right, see you next time.